In this video, we'll explore how to use PyTorch for machine learning. First, we import the main PyTorch library using import torch. This library provides the core functionality needed for tensor operations, mathematical computations, and deep learning tasks. PyTorch tensors are similar to NumPy arrays, but they can also run on GPUs for faster processing. Next, we import the torch.nn module as NN. This module contains the building blocks required to create neural networks, such as layers, activation functions, and loss functions. Using the alias NN makes the code shorter and easier to read. After that, we import torch optim as optim. The optimization module provides algorithms like SGD and atom, which are used to update the model's parameters during training so the network can learn from data more effectively. We create a tensor named using torch tensor 1.0, 2.0, 3.0. A tensor is the fundamental data structure in PyTorch and is similar to an array or matrix. In this case, it is a one-dimensional tensor containing the values 1.0, 2.0, and 3.0. Next, we create a tensor named b using torch ren33. This function generates a 3x3 tensor filled with random numbers drawn from a standard normal distribution. Random tensors are commonly used for initializing neural network weights or testing models. After that, we create a tensor called C using torch 0s 2, 3. This creates a 2x3 tensor where every element is 0. Zero tensors are often used as placeholders or for initializing variables before training. Finally, we create another tensor named D using torch 1s 2, 3. This function generates a 2x3 tensor filled entirely with 1s. 1s tensors are useful for testing operations, creating masks, or initializing certain model parameters. First, we create two tensors named x and y using PyTorch. The tensor x contains the values 1.0, 2.0, while y contains 3.0, 4.0. These tensors will be used to demonstrate basic tensor operations. The statement prints plus y performs element-wise addition between the two tensors. Each value in x is added to the corresponding value in y, producing the result 4.0, 6.0. Next, prints y performs element-wise multiplication. This means each element in x is multiplied by the element in the same position in y. The result is 3.0, 8.0. The expression prints at y calculates the dot product of the two tensors. In a dot product, corresponding elements are multiplied together and then summed. The calculation is 1.0x 3.0 plus 2.0x 4.0 equals 11.0. After that, printx sum computes the sum of all elements in tensor x since x contains 1.0, 2.0, the result is 3.0. Finally, printx mean calculates the mean average of the elements in x. The average of 1.0 and 2.0 is 1.5. This operation is commonly used in data analysis. We create a 4x4 tensor named x using torch random4 in PyTorch. The random function generates random values from a standard normal distribution. So the tensor will contain randomly initialized numbers arranged in 4 rows and 4 columns. Next, printx view 16 reshapes the tensor into a one-dimensional tensor containing 16 elements. The view function changes the shape of the tensor without changing its underlying data. Since a 4x4 tensor contains 16 total elements, it can be flattened into a single row of length 16. After that, printx reshape to 8 reshapes the same tensor into a 2x8 structure. This means the tensor will now have 2 rows and 8 columns while still containing the same 16 values. The reshape function is another way to change tensor dimensions and is often more flexible than view, because it can handle cases where memory layout changes are required. Reshaping tensors is an important operation in deep learning, because data often needs to be reorganized before being passed into neural network layers. We create a tensor x using PyTorch and set its value to 2.0. We also enable requires grad equals true, which tells PyTorch to keep track of everything done with this tensor, so it can later compute how it affects the final result. Next, we define a new value y using a combination of operations on x. PyTorch automatically records each step in the background. building a system that remembers how y was created from x after that, we call y backward. This tells PyTorch to go back through all the recorded operations and calculate how much y changes when x changes. This process is called automatic differentiation and is a core part of training neural networks. Finally, we print xgrad, which shows the result of this calculation. PyTorch stores this value inside the tensor, and it represents how strongly x influenced y. In this case, the output will be tensor 7. This process is very important in deep learning, because it allows models in PyTorch to automatically learn from data without manually calculating derivatives or updating parameters. First, we create a tensor x using PyTorch with 3 random values using torch random 3, and we set requires grad equals true. This tells PyTorch to track all operations involving x so that it can later compute gradients automatically. Next, we compute y equals x2. This means every value in x is multiplied by 2. PyTorch records this operation in the background as part of its computation graph, so it knows how y was created from x. After that, we compute z equals y sum. This step adds all the elements in y into a single value. So instead of a vector, z becomes one number representing the total sum. Then we call z backward. This is where PyTorch performs backpropagation. It works backward through all the recorded operations and calculates how much each element in x contributed to the final result z. Finally, we print xgrad. This shows the gradient values stored in x since each element in x was multiplied by 2 and then summed. Every element receives the same gradient value. This code defines and uses a simple neural network built with PyTorch. The model is a basic feed-forward neural network with one hidden layer. It takes input data with 10 features, processes it through a hidden layer with 20 neurons, applies a ReLU activation function to introduce nonlinearity, and then produces an output layer with 2 values. After defining the model, we create an instance of it. This means the network is now ready with initialized weights and can process data. Then, we create a sample input batch containing 5 data samples, each with 10 features. When this input is passed through the model, it performs a forward pass, meaning the data flows through all layers of the network step by step. Finally, the output shape becomes 5, 2, which means for each of the 5 input samples, the model produces 2 output values. This structure is commonly used in tasks like classification, where the output might represent scores or probabilities for different classes. Overall, this example shows how a simple neural network is built and used in PyTorch to transform input data into meaningful outputs. This code shows a complete training and evaluation loop for a simple neural network using PyTorch. First, we create a dummy dataset. X contains 100 samples, each with 10 features, and Y contains binary labels, 0 or 1, for each sample. This simulates a simple classification problem. Next, we define the loss function and optimizer. The loss function used is cross-entropy loss, which is commonly used for classification tasks because it measures how well the model's predictions match the true labels. The optimizer used is stochastic gradient descent, SGD, which updates the model's parameters based on the computed gradients. Then, we start the training process by setting the model to training mode. For a few epochs, the model goes through the following cycle. It makes predictions on the input data, calculates the loss by comparing predictions with the true labels, computes gradients using backpropagation, and updates the model's weights using the optimizer. This process gradually helps the model learn patterns in the data. After training, the model is switched to evaluation mode. In this phase, gradients are not calculated because we are no longer training the model. Instead, the model simply makes predictions on the data. Finally, we compute accuracy by comparing the predicted classes with the true labels. The predicted class is chosen as the one with the highest output score for each sample. The final accuracy value shows how well the model performs on the data set. You've now completed the basics of a PyTorch tutorial. In this walkthrough, you learned how to create and manipulate tensors, perform basic operations, and understand how gradients work through automatic differentiation. You also built a simple neural network, passed data through it, and saw how training works using a loss function and optimizer. Finally, you evaluated the model using accuracy to measure its performance.